Today we are going to discuss vector analysis. We'll start with definition of scalars and vectors. Then we'll see what are the axial vectors and polar vectors. We'll see the different ways of representation of vectors. We'll also discuss the different terms which will be used in this particular chapter. Along with that, we'll also discuss different cases wherever it is applicable. First of all, let's recall what are physical quantities. Physical quantities were those which can be measured. That means anything which cannot be measured will not be termed as physical quantities. Then these physical quantities we classify in two categories: scalars and vectors. Scalars are those physical quantities which require only magnitude for their complete specification. So anything which will require only magnitude, like if you are supposed talking about the mass, so just telling the quantity of the mass is sufficient. Similarly, if it is the time, in that case also it is sufficient to just mention what is the duration of the time there. So those will be called as scalar quantities. And if you take their examples, we have mass, we have distance, we have time, then it is the speed, it is the density, that is also a scalar quantity. So all these are scalar quantities. Here we can also take work done, we can take energy, any form of energy, that all will be scalar quantities. And then for vectors, vectors are those physical quantities which require magnitude and direction both for their complete specification, and they must obey the laws of vector addition. This is very important. There may be physical quantities which will have magnitude and direction both for a given case, but as they do not obey the laws of vector addition, they are taken as scalars, not as vectors. Example of the vectors, if you consider, we have a displacement, then it is your velocity, acceleration, then we can take momentum, we have force. Okay, all these are there, like you have the torque also there. So all these are the examples of the vector quantities. Let's see, we have said that they must obey the laws of vector addition. Okay. Suppose we take one example, that we have a circuit where we have a resistance of 6 ohm and it is connected to a source of 12 volt. And these are the points, say A and B. It is asked what is the current in the circuit. So current magnitude, if you take, then we know from Ohm's law that I is equals to V by R. So in that case it will be equals to 12 by 6, that is 2 ampere. So 2 ampere will be the current in this circuit. And if it is asked what is its direction, then we can say that it is from positive terminal to negative terminal of the battery through external circuit. That is the conventional direction of the current which we take. So for this, it is positive to negative, so it will be from A to B. So the direction will be from A to B. So this is the direction of the current in this circuit. Now if we change the polarity, then the direction of the current will just get reversed. Because now current magnitude will remain 2 ampere, but now it will be flowing from B to A. And if it flows from B to A, direction has changed. That means for a specific case, it has magnitude 2 ampere. It has a specific direction, either it is A to B or it is B to A. But still we do not say or take electric current as a vector quantity. Electric current is a scalar quantity. So electric current This is an example of a scalar quantity. Why? Because it does not obey the laws of vector addition. Also, we have used the word vector addition. Does the additions are different? That means, is the addition for a scalar is different from addition of vectors? Yes. If you take a scalar addition, that means you take physical quantities which are scalar quantities, and if you just add, that is the normal addition which you are doing. Like if suppose you take 3 kg of sugar and 4 kg of sugar, no matter how you mix them, in whatever parts you are mixing, the total quantity will remain 7 kg. Similarly, if suppose you take any other quantity, say we are taking water and we take suppose 5 liters of water and add it to 2 liters of water. In that case, the total quantity will remain 7 liters. No matter how you are adding them. You are taking first 5 liters and then 7 liters, or some amount of water from 5 liter container where you have kept that, and then you are taking some amount from 2 liter container. Total will always remain 7 liters. But for vectors, if you take the sum of 2 vectors will be equal to, or its value will range basically from maximum to minimum depending upon what is the angle between them. That means the resultant of the 2 vectors will be depending upon not only just on the magnitude of the individual vectors but also on the angle between the 2. For example, suppose you have a force of 3 Newton and 4 Newton acting on a body. If you have suppose 4 Newton force and 3 Newton, the resultant will be 7 Newton. If I take the force of 4 Newton in this direction and 3 Newton in opposite direction, the resultant will be 1 Newton. If you take 4 Newton and 3 Newton, suppose it is 3 Newton here, 4 Newton here, the resultant will be given by a force of 5 Newton. That means its magnitude is changing of the resultant from 7 to 1 Newton, and whatever be the angle between the 2. If the angles are changing, then the magnitude will range from 1 to 7. This is for vector quantities. But now, if you consider, suppose we have a wire through which 4 ampere of current is going, another is there through 3 ampere is going. This is the wire through which the resultant current will go. So this one will remain 7 ampere no matter what is the angle between the 2. Whether you put the wire like this, another is this, or you put this 3 and this 4. Whatever way you keep, it will always remain 7 ampere. That means it is not depending upon the angle between the 2 wires which are carrying that current. So it is just obeying a scalar addition, not the vector addition. That is why electric current is taken as a scalar quantity. There are a few more terms for which you should be very careful. One more term is there, that is called as the electric current density. Electric current density is a vector quantity. Remember, electric current is a scalar. Density term is a scalar. But if you take electric current density, which is basically electric current per unit cross section of the conductor through which it is flowing, that is, we call it as electric current density. Electric current density is a vector quantity. Of course, you will come across the expression for electric current, which is also represented as a scalar product of electric current density and vector area. Even remember that normal area, if you take it, is a scalar quantity. But if you consider vector area, this will be a vector quantity. Vector area will be basically one surface whose area we are taking, and its direction will be perpendicular to the plane of that particular surface. So magnitude will be equal to the area enclosed there, and direction will be perpendicular to that. Either it may be into it or it may be out of it. So these are the examples of scalar and vector quantities. We have seen that physical quantities we can classify in two categories. One was the scalar quantities and other was vector quantities. Even in the vectors you'll find there are two categories. One is called as the polar vectors, other is called as the axial vectors. So let's take what are polar vectors. Polar vectors will be the one which have fixed starting point, or they have a specific direction of application or fixed direction of application. For example, if suppose you take displacement, in that case it will have a particular fixed point from where it is starting, and in a particular direction it will be acting there. Or suppose you have a force acting on a body. So the force acting on the body may be shown that it is acting in this direction or the other direction there. This is suppose your F1, this is your F2. So there you have a fixed starting point, or at least even if the starting point is not specified there, at least you know what is the direction of its application. We can say that it is acting in this direction or it is in this particular direction. Wherever it is a translational direction there assigned to them, in that case it will indicate a polar vector. Like all these, if you take a displacement, velocity, then it is your force. All these will be the examples of polar vectors. But another will be that is called as the axial vector. Axial vector will be the one which will be associated with the turning effect there. That means basically rotational motion, you will come across that. One vector might be acting in one direction, other might be acting in the other direction, but the impact of that will be in some other direction. So there it is called as the axial vector because it acts along the axis of that. Say for example, if you have a body or a particle moving along a circular path, it has its angular displacement in one direction. But if you consider the direction of the angular velocity, it will act along the axis of it. Similarly, if you take angular acceleration there, it will act in one particular direction. Or suppose if I take, we have an angular momentum, which is given as r cross p. Position vector will be in one direction of particle. Suppose its velocity is in one direction. Okay, so in that case, the angular momentum will have one specific direction that will be along its axis. So there we take its the vector which is acting along one particular direction or along its axis. Here you will not have a starting point there. You can't say that it is starting from this point. It will just act along one particular direction. And in rotational motion there, basically you will come across this type of term. Even if you take the torque, which is given as your r cross f. So this is also an example of your axial vector. So the example of the axial vectors you can take as the angular velocity, angular acceleration. It may be your torque, or you can take angular momentum. All these, because they will be acting along one particular direction or along that particular axis there. So they are called as the axial vectors. So these are the polar and axial vectors. There are some physical quantity. Their magnitudes are different in different directions. And for them, you cannot assign any specific direction to them. So such physical quantities are called as the tensors. So tensors will be those physical quantity which do not have a specific direction there. They have the magnitude of different value in different directions. So as they do not have any specific direction of application there or their impact, we call them as tensor. Like here, moment of inertia, if you take, this is a tensor quantity because its direction, in different direction, its value will be different. You take particular body, you find its moment of inertia, then its moment of inertia value will be different for the same body in different direction. Similarly, if you take the pressure exerted also has different value in different direction. So the pressure is also taken as the tensor. So those physical quantity which do not have any specific direction there, or they have the different values in different direction, we call them as tensor. Let's now take up representation of vectors. How do we represent the vectors? For that, we have one graphical representation, other will be the symbolic representation of vectors. So first let's take graphical representation. In graphical representation of vectors, we draw a line parallel to the direction of the given vector, and we'll put an arrow to represent its direction. The length of that line must be proportional to the magnitude of the vector. So suppose if I have to represent a displacement of say 4 km in north direction, we have a displacement of 4 km in the north direction. So to represent that, suppose we take this K and axis here. This is suppose the origin. This is representing suppose east direction. This is suppose the north direction. Okay, x-axis we have used to represent east. This is north. Obviously, this will be your west and this will be south. Now, then we'll take a particular scale to represent it. So suppose I use a scale that 1 kilometer will be represented by 1 centimeter. Therefore, we need to draw a line of 4 centimeter length in the specified direction. So if it is the north direction, first of all, I will draw a line in the north direction. Length of this line should be proportional to the magnitude. So I will take a length of 4 centimeter to represent 4 kilometer. So there will be a line of 4 centimeter to represent 4 kilometer. Then we'll put an arrow to represent its direction. Arrow is must, because if you are just drawing a line in this direction without arrow, we do not know whether the movement is in this direction or it is in this direction, whether it is towards north or towards south. So for that we put an arrow. If our starting point is here, if I have to show in the north direction, I will show line in this direction. If it is 4 kilometers south from this, if I will represent line in this direction. So we'll put or we'll represent 4 kilometer displacement in north direction like this. Suppose the body further moves through 3 kilometer in east direction. So from here, we'll draw now a line in the east direction, and the length of that should be proportional to its magnitude. That means I will take a 3 centimeter length. Again, we'll put an arrow. This represents now displacement of 3 kilometer in the east direction. Suppose it further goes through 5 kilometer in northeast direction. So from here, this will be representing the northeast direction. So I will draw a line of 5 centimeter in this direction. So this will represent now displacement of 5 kilometer in the northeast direction. So basically what you have to do, you have to draw a line in the direction of the given vector. The length of that line should be proportional to the magnitude of the vector, and we put an arrow to represent its direction. This is how we represent a vector in the graphical representation. In the graphical representation of vectors, suppose we have shown a vector like this. We have drawn a line and we put an arrow there. Length of this will be proportional to the magnitude of the given vector. This is the starting point. We call this as the tail of the vector. This is called as the head of the vector. This is the head of the vector. Now, tail is basically representing the initial point. Whereas this is called as the terminal point. That means tail will represent initial point of the vector and head will represent the terminal point of the vector. And this one, the length of this is called as the body of vector. And what does this body of vector will represent? This will basically represent the magnitude of the vector. So this is basically the magnitude of the vector. So this is the graphical representation where we show tail, we talk about the head, we talk about the body of the vector. All have a specific meaning there. Just like this is the initial point, this is the terminal point, this is the magnitude of the vector which is represented by the body of the vector. So this is their graphical representation of vectors. Next is symbolic representation. How symbolically we represent a vector. Suppose we have a vector A. We have a vector A. We represent this one as the symbol A with an arrow over it. Arrow we use to specify that this is the vector quantity. Similarly, if I have to represent vector B, then over its symbol B, we'll put an arrow. Similarly, if it is your vector PQ, this will be represented as PQ with an arrow over it. So this is how we represent a vector quantity in writing. Similarly, if suppose you have M vector A, this represents that this M is a scalar quantity because there is no arrow over it. And A has an arrow over it, so it is a vector quantity. It may be just like 3 times force, 2 times any particular displacement, suppose. Okay, so this is how we represent there symbolically. And one more thing there, if you go through the old edition books there or foreign authors book there, they used to represent vectors not by this symbol with an arrow over it, but they use dark faced letters or bold letters there to represent vector. What does it mean? There you'll find that this vector A, which we have written like this, it will be written with a dark faced letter or bold letter. So it will be written like this. Similarly, vector B will be written as a dark faced letter like this. If it is your PQ vector, this will be written as your P and Q. That is the dark faced letter there. No arrow, but it is just a dark faced letters. Similarly, if I have to write this M vector A, there in those books you'll find that it will be written as your M and then it is your dark faced letter. It is written like this. So wherever you find some dark letters written there in any text there, especially dealing with the physics there or vectors there, so there just understand that that is representing a vector quantity. Now why they have used, or why you do find in old edition books like this? But because now in new edition books, if you see everywhere, whether it is written there or we are writing the way vectors, at the same way it is written there in the books also. In new edition books also you'll find they all have used this type of symbol to represent vector. That is the symbol with an arrow over it. Probably in old edition books there, if you see, when they were printed there, that time the printing was done with the blocks there. They have the different blocks there, and in those blocks they used to put the letters which they want to print. So these are the different printing blocks there. And suppose if it is just like they have to write this, so they will put the letter T here, H here, I and S. And if it is your each, they will just leave a one space and then it is written like this. Between two lines, they leave a small gap there, and then it is written like printed here. They put the blocks in this one. Now just imagine if there is any vector term is coming. So if they write it like this, if they put it A here, they will have to put arrow here. That means if it is just written like, suppose in any line, it is written as A, B, C, D, E, and then it is your E, F, G, H, I, okay, L, M, N, O. It is just like this. So there is a proper spacing between the two lines. But if they have to put an arrow there, in that case, what will happen? One full line will be just wasted. Like suppose if I have to put, suppose vector A. So if it is your vector A here, arrow will be here. So in printing, what you'll find, once it is printed on the sheet, you'll find it is printed like this. This is having a small, large gap there. Moreover, between two lines, because if suppose it is now this X, Y, Z, M, N, so here you'll find unnecessary gap there. So there, if they print in that way, there will be unnecessary gap between the lines. And this is just like the wastage of the paper there. So it was convenient for them to use a dark faced letter, because if they are using dark faced letter, they don't have to put the arrow there. So they will simply put a dark faced letter there and they will print. So they can save this particular line. They can print whatever they have written. So that is why they have used dark faced letter at that time. But nowadays, if you consider, the printing is done there by first framing the text there on the computer. So when you are using it in computer there or typing in computer, you can easily change the gap between two lines. If there is a gap to be changed between these two, or gap between this arrow notation and A there, or this line, you can easily change the spacing between two lines. Or now we have the fonts also for the vector symbol. So we can easily use or insert the font for the vector symbol. So we can just put it there and we can save the pages. So that is why nowadays when the printing is done in a modern way, we can easily put the arrow there. We can reduce the gap between the lines without wasting paper. So that is why we can easily use this way as we are writing. Because for writing, for us it is more convenient there to just write any vector with an arrow over it. For them, it was convenient to use dark faced letters in printing. But when they are writing, they will just put an arrow over the symbol. For us, it is difficult relatively to put dark faced letter or write dark faced letters. Because if you are writing anything and you are putting arrow there, so like here, if I have to write vector B, for us it is more convenient to write symbol B with an arrow over it, where instead of making it bold or dark. So that is the reason why in printing they are now using this symbol, not the one which has been used earlier there. And for writing also, it is the same way we are following. That means for representing any particular vector with over its symbol, we just put an arrow. So in most of the books there, which is available, you will find the same way as you are writing in copy. It will be printed there in your book also, or you will find in the books also. But only in old edition books, if they are, there you may find bold letters used for representing vectors. Of course, some very popular and common books of foreign authors are there. In the new edition, you will find that they have used the symbols like this for vectors. Whereas in old edition books, you will find bold-faced letters used. So this is for the representation of vectors. Now let's discuss some of the terms which will come across in this chapter. First one is negative vector. Negative vector of a vector is the vector having same magnitude as the given vector, but its direction is just opposite to the given vector. For example, suppose we have a vector A represented like this. That means it has this much magnitude and it is in one particular direction there. So another vector of same magnitude but in opposite direction, this will be representing the negative vector B. Suppose I call it as the vector B. So this vector B will be minus vector A. That means it is basically negative vector of A. So this is the negative vector. This is equal vectors. Two vectors are said to be equal vectors if they have same magnitude and same direction. So suppose if you take two vectors and we say that vector A magnitude is same as vector B and directions are also equal, in that case they will be called as the equal vector. Like suppose if I have this as vector A, this is another vector, say B. Both have same magnitude and same direction, so we can call them as the equal vectors. Or if this is a vector A, suppose it is the same magnitude. This is the vector C. This C is not same as the vector A or B because their directions are different. Although magnitude wise, suppose it is same, but still they will not be equal vector. But suppose if I represent another vector D, which has the same magnitude as the vector C and directions are also equal, so here vector C will be equal to vector D and these two will be equal vectors. So for equal vectors, we can have one pair as A and B, another pair it may be your C and D. Co-initial vectors. Two vectors having same initial point, they will be called as the co-initial vectors. So if I have a vector A, another vector B is there, both have the initial point at one particular point. So these two will be called as the co-initial vectors because their initial points are at one particular point. So they are called as the co-initial vectors. Similarly, we have another term that is your coterminous vectors. That means the vectors having same terminal points, they will be called as the coterminous vectors. Like suppose you have vector C, suppose here, and this is another vector D. The two have the same terminal point. So these two will be called as the coterminous vectors. So vectors having the same terminal point will be called as the coterminous vectors. Vectors having same initial point, they will be called as the co-initial vectors. Let's take collinear vectors. Two vectors are said to be collinear if they are acting along the same line. Now that means it's not necessary that if it is your vector A and this is vector B, they are along the same line. Of course, they are collinear. But any other vector also, if it is suppose C, it is parallel to vector A or B, these two will also be called as the collinear vectors. So the two vectors having the same direction, they may or may not have equal magnitude. They will be called as the collinear vector. They may or may not act along the same line. Then they are called collinear vector. The two vectors may be parallel to one another. Angle between the two vectors must be 0 there. In that case, they are acting along the same line. Coplanar vectors. Vectors lying in the same plane, they are called as the coplanar vectors. So suppose you have vector A here. this is another vector B, this is C, all are lying on the plane of this board. So they all are coplanar vectors. Here, suppose I represent one vector along, say, x-axis. This is suppose y-axis, this is z-axis. Suppose I have a vector A along x-axis. Another vector B is along y-axis. So they are lying in the xy plane. So they will be coplanar in that. But if you consider another vector, suppose C, all are not coplanar. But vector A and vector C, they are lying in one plane, they are coplanar. Vector B and vector C, they are in one particular plane, yz plane, in that case they are also coplanar. So you have to see that the two vectors which we are taking, two or more than two, if they are lying in the same plane, then they are called as the coplanar vectors. Next is your localized vector or fixed vector. Next is localized vector or fixed vector. The vectors whose initial point is fixed, that will be called as the localized vector, and they will be your fixed vectors. If you have one vector and one end is fixed, whatever direction and magnitude we are representing, if this end is fixed, then it will be your fixed vector or localized vector. But if suppose we take non-localized vector, there if the ends are free, in that case they will be called as non-localized or free vectors. You have one vector there, you can shift it to other position. Another vector is there here. This is the vector C. If I shift this one to some other position there, in that case they will be like your free vector. You can easily shift it. You have not fixed its one end there at one particular point. So those vectors will be called as the free vectors. Another vector is position vector. Position vector will be, this will be giving you the position vector, that is a vector related with the position of a particular particle or a body at a particular instant of time. Suppose we take a Cartesian system. This is suppose x, this is y, this is z. A particular point is at a particular position. Suppose P is the point. It is having a coordinates, say x1, y1, z1. This is its position at a particular instant of time. So a vector joining this particular point from the origin or the reference point, that will be called as the position vector of the particle at that particular instant. So if I take a vector, this is your OP. This OP vector is the position vector of the particle or the point P. Similarly, if suppose after some time point P is suppose here, or it will be represented by your P dash. This is the another position of the particle after a particular instant of time or after some instant of time. So there, if you now join this particular one to the origin, so this is OP dash is the position vector of the particle at that particular instant. Suppose it is at this position at instant T dash, and here the coordinates are say x2, y2, z2. So in that case, this particular vector will be representing your position vector. Of course, if you represent this position vector of the particle in terms of Cartesian coordinates or in Cartesian system, we can write it as your x1 I cap, y1 j cap, z1 k cap, like that. Similarly, OP dash will be x2 I cap, y2 j cap, z2 k cap, like that. Another is the displacement vector. This will give you the net displacement or shift of the position of the particle in a particular interval of time. Say for example, we have assumed that the particle is at point P at an instant T. In time T dash, it is at position, or at time T dash, it is at a position P dash. So its position vector is your OP dash. And this particle has shifted in this direction. So that is PP dash. This will represent the displacement vector. So this is the displacement vector of the particle in the duration delta t in which this change of the position has taken place. So this PP dash will be the displacement vector. Displacement vector. So this is the displacement vector of the particle. Let's now take unit vector. Unit vector is a vector having magnitude unity. A vector whose magnitude is 1, that will be called as unit vector. How we get that vector? Suppose you have a vector A. If you divide this particular vector by its own magnitude, so if you are dividing it by its own magnitude, then we get a vector whose magnitude will be 1, because the vector itself have been divided by its own magnitude. So its magnitude of the resultant one will be 1. However, the direction will be same as the given vector. So this will be represented as your A cap. This is the symbol which we are using to represent here. First of all, this is unit vector A. And how we have represented? We have represented it with symbol having a cap notation. This particular term, now we represent or call it as A cap, or we can call it as A hat or A caret. This is basically term used for this cap notation. Either you can call it as cap or hat or caret. So this is how we represent unit vector. Similarly, suppose you have vector B. So unit vector B will be represented as your B cap, and this is basically vector B divided by its magnitude. So this way you can get the unit vectors. Do remember one thing, vector A cap or vector or B cap, these two are unit vectors. Their magnitudes are equal and it is equal to 1. But they are not equal vectors, because the vector A may be in one direction, vector B may be in another direction. Like suppose this is your vector A direction, this is your vector B's direction. So unit vector A will be in this direction itself. Similarly, unit vector B will be in this direction. These two magnitude wise will be equal, A cap and B cap, but directions as they are different, so they are not equal. Okay, magnitude wise will be equal, but A cap is not equal to B cap in general. Of course, if the two are in the same direction there, vector A and vector B, then they may be equal. There are some standard symbols used for unit vector. So it is like I cap, J cap, K cap. These are used to represent unit vectors along x-axis, y-axis and z-axis. I cap is the unit vector along x-axis, J cap is unit vector along y-axis, K cap is unit vector along z-axis. So if you represent it in the Cartesian system, suppose this is your x-axis, y, and this is your z-axis, I cap will be in this direction along x-axis, J cap is along y-axis, K cap is along z-axis. So it is like this. These are the standard symbol we are using in vectors there, especially when you want to represent the vector in Cartesian form. Another term is there, zero vector. This is zero vector, or this is also called as null vector, or it is also called as void vector. So zero vector is a vector having magnitude 0. So that will be called as the zero vector, or it is also called as the null vector or void vector. How do we get that? If you have one particular vector acting in one direction, if you take its negative vector and take their sum, then you will get a zero vector. So for example, you have a body on which we are applying a force of 5 Newton in one direction. So if you have a body, on that you are applying a force of 5 Newton in this direction. And then we apply another force of same magnitude. This is suppose your F1, this is your F2. So the two forces are acting on the same body but in opposite direction. So what is the resultant? If I take suppose F1 plus F2, how much it will be? This is your plus 5, this is say minus 5. Can we write it just 0? If you are writing it as 0, that means you are representing that it is having a magnitude 0. But is it a scalar quantity? The two forces are acting on the body. Resultant force has a magnitude 0, but it is a force which is a vector quantity. So this will be your vector, zero vector. So that is the zero vector there. So if you consider two vectors acting on a body and giving the resultant as 0, they give 0 vector. So that will be your 0 vector there. So few properties are there of 0 vector. First is 0 vector when added to or subtracted from a given vector leaves the vector unchanged. That means if you have a vector A, you are adding 0 vector to that, it will remain vector A. If you have vector B and from that if you are subtracting 0 vector, it will remain vector B. So 0 vector when added to or subtracted from a given vector leaves the vector unchanged. This is the first property. Second property is 0 vector does not have any specified direction. 0 vector can be in any direction. Now how we get that? When you do addition of vectors, then you will find that if the two vectors are acting along the same direction, the magnitude of the resultant is given by sum of magnitude of individual vectors. Like suppose if you have a force of 4 Newton in one direction, 3 Newton of force is also acting in the same direction on the body, the resultant will be 7 Newton. So here, if you now consider that you have vector A and you have added 0 vector to that, so to vector A you have added 0 vector, what you get? Vector A. This has magnitude A, this 0 vector has magnitude 0, and the resultant also have the magnitude A. It means the magnitude of the resultant is same as the sum of the magnitude of the individual vectors. That means the vector A and 0 vector are in the same direction. If you take from that concept that resultant of the two vectors acting along the same line has magnitude same as the sum of the magnitude of the individual vectors. So here it will indicate vector is in the direction of vector A. If I now take vector B and add 0 vector to that, it will remain vector B. So this will indicate that 0 vector is in the direction of vector B. A and B may be in different direction. So what we can conclude from that? 0 vector does not have any specified direction. It can act in any direction. So that is the second property of the 0 vector or null vector.